Hello, everyone. This is the fourth and final part of my Chapter 7 lecture notes for Physics 211. Please refer to page 12 of your notes. We're going to be talking about the interrelation between force and potential energy in this section. So, in one dimension, a conservative force can be obtained from its potential energy function using the force of that conservative force is equal to the negative of the derivative of the potential energy with respect to x. Very important to note that this is in one dimension. So if you're dealing with force just in x or in y or in z, you can take the derivative of that function with respect to x or y or z to give you the force function. In regions where the function of potential energy, ux, changes most rapidly with x, this corresponds to a larger force magnitude. The sign here is also important. So when force is in a positive direction, the potential energy is decreasing. This is basically a way of saying that the potential energy is being converted into force and being converted into sort of positive work, if you will. So you're getting a transfer of potential energy into kinetic energy or some other kind of energy, and this means that your force is positive. So again, to rephrase that, when force is in the positive direction, the potential energy will decrease with increasing x. And a conservative force always acts to push the system toward lower potential energy. So in other words, if I have this cap, and this has been a very handy cap, or rather this mouse, and it has a particular potential energy, the force of gravity is going to act in the downward direction, which means that it is going to reduce the potential energy. So the force of gravity reduces potential energy, meaning that a conservative force always acts to push the system towards lower potential energy. In 3 dimensions, the components of a conservative force can be obtained from its potential energy function using partial derivatives. So for instance, the force in the x direction corresponds to the negative of partial u partial x. The force in the y direction equals the negative of partial u partial y. And the force in the z direction is equal to the negative of partial u partial z. When we take the partial derivative of u with respect to each coordinate, multiply by the corresponding unit vector, and then take the vector sum, this is something called the gradient. And this is something that you'll see in other physics classes and in mathematics classes. This is the gradient. And what that is partial u partial x times I cap. So this is, again, the x component of a force vector, plus partial u partial y j cap, so this is corresponding to the y component of the force vector, and partial u partial z k cap corresponding to the z component of the force vector. And remember, forces are vectors. So you're looking at these individual components, and that is done by taking partial derivatives. Right? So let's take a sample problem. We have a small block with a mass of 0.04 kilograms moving in an xy plane, so there's no z. The net force on the block is described by the potential energy function, u is a function of x and y, of 5.85 joules per meter squared, x squared, minus 3.55 joules per meter cubed, y cubed. So once again, that's 5.85 joules per meter squared x squared minus 3.55 joules per meter cubed y cubed. And it's asking us first, what is the magnitude of the acceleration of the block when it is at the point x equals 0.23 meters, y equals 0.54 meters? And we are to express our answer with the appropriate units. So what we do to find the force vector is to take the appropriate derivatives, or rather the appropriate partial derivatives. So we have partial x for this x component, so that's for that guy, and then partial y for that component there. Now, when you're dealing with partial derivatives, let's say that, for sake of example, we had like a z term here, z squared. When you're doing a partial derivative, you should treat anything that is not being derivatized, if you will, as though it is a constant. So z squared in this case would be a constant, and we're taking the rest of this derivative. And again, assuming that that is just, we're treating it as though it were a constant, meaning that, well, that's what we're doing when we're doing a partial derivative. Anyway, in this case, that doesn't happen. We just have the force in x being a function of x and the force in y being a function of y. So we can treat this partial derivative just like an ordinary derivative, really, and we execute that derivative. So this 2 comes out in front here. We end up with 11.7 joules per meter. Again, we're getting rid of that m there. And then we have x here. So that's as a result of taking that derivative. And plus 3 times 3.55, so 10.65 joules per meter squared times y squared, again, as a result of taking this derivative. Incidentally, you'll notice that this sign is opposite to what we see up here, and this sign here is also opposite to what we see up here. And that is because, as you will recall from the previous slide, the force is equal to the negative of the gradient. Okay? And then we'll say u x y. So again, that's why the sign switched between the function that we're given and the function that we are actually evaluating. All right? So then we substitute for x and y. We are given x is equal to 0.23 meters, y is equal to 0.54 meters. So that goes in for x and in for y. We go ahead and note that you want acceleration, which is actually force over mass. So you can divide both I cap and j cap by the mass. So you just divide through by m here. You're given that the mass is 0.04 kilograms. So that goes on the bottom here. We already have something here in the denominator in each case in meters. So now we're going to add a unit of kilograms. So 0.04 kilograms times meters, because it was already in joules per meter. So we have 2.70 joules. That's the result of evaluating this part of the equation over 0.04 kilograms times meters I cap plus 3.11 joules over 0.04 kilograms times meters times j cap. We go ahead and evaluate, and we find that the acceleration is equal to negative 67.5 joules per kilograms times meters I cap plus 77.8 joules times kilograms times meters j cap. Now, this is kind of a weird unit. When was the last time we saw joules over kilograms times meters? And acceleration we're expecting to see in meters per second. So just as kind of a sanity check, and to make sure that we're not making things up, we want to make sure that this unit here, joules over kilograms times meters, rather, actually translates to what we know acceleration to be, which is meters per second squared. How do we do that? Well, if we look back at the notes from the previous chapter, we remember that 1 joule is equal to 1 Newton times 1 meter, 1 Newton times meter. And 1 Newton times meters, using the definition of what a Newton is, which is a kilogram times meters over second squared times meters. So again, this is this part here. That's 1 Newton. And then we're multiplying it by meters. And we find that the definition of the joule is 1 kilograms times meters squared over seconds squared. All right. So let's double check and make sure that we've got the right units. So a joule over a kilogram times a meter is 1 kilogram times a meter squared over a kilogram times a second squared times a meter. Well, we can cancel out one of these meters here. We can cancel out the kilograms, and what we're left with is 1 meter per second squared, or 1 meter over second squared. So this is in fact the correct unit. This all works out, and we know that we didn't make some sort of mistake when we were actually executing this problem. Okay? So now we can go ahead and we can rewrite this with the proper units as A equals negative 67.5 meters over second squared I cap plus 77.8 meters over second squared j cap. We are asked for the magnitude of the acceleration. So to find that magnitude, we just use what we've done before to find the magnitudes of vectors. So we have the x component squared plus the y component squared. We take the square root of this sum, and we find that acceleration, or the magnitude of acceleration, is 102.7 meters per second squared. Sorry, there should be a squared sign here. All right. So there's our answer for part A. In part B, we're asked for the direction. So in other words, we want to put this in polar coordinates. I'm going to put the squared back in there for a minute. So to find this direction, what we can do is say, all right, the y vector is pointing upwards, or the y component of this vector, rather, is positive, and it's 77.8. The x component of the vector is negative, and it's 67.5. We are left with this triangle, and we want to find this angle. This angle is what we're going to call theta. So from the x-axis all the way over to this resultant vector, which is in red. To do that, we can find this angle here, phi, and simply add 90 degrees to it. So theta equals 90 plus phi, which is 90 plus the tangent inverse of the opposite over adjacent. So opposite is 67.5, adjacent is 77.8. So we take that tangent inverse, and we find that this angle of theta is 130.9 degrees. So that's 130.9. All right, and that wraps it up for part B. That's fairly straightforward. All right, now we're going to take a look at energy diagrams. So an energy diagram is a graph that shows both the potential energy function, U as a function of x, and the total mechanical energy, E. So the figure illustrates the energy diagram for a glider attached to a spring on an air track. So what's happening is this spring is going this way. So basically you've got a glider that's at a neutral position, some energy has been added to it, and it just oscillates from one position to the other. It goes springy, springy. What allows us to do that? Well, because it's on an air track, we can neglect the presence of friction. There's also not going to be friction in the spring in this particular example. Remember that because energy is conserved, because this is a conservative force, as this is moving, the kinetic energy here gets transformed into potential energy until such time as the glider stops. The potential energy is then released, turned back into kinetic energy, which then eventually compresses the spring. Again, there's a storage of potential energy, and it goes springing backwards. And in the graph, the limits of the point of the motion are in negative A and positive A. So we're only talking about this particular region that we've outlined here. And you can see that the potential energy is actually on this kind of very nice curve here. So the distance from this curve upwards to the total amount of energy in the system is equal to the kinetic energy, whereas everything that's kind of underneath the curve here is equal to the potential energy. And you'll notice that at point O, the potential energy is 0, and all of the energy is kinetic. Similarly, at this point, at negative A and positive A, all of the energy is stored as potential energy, and none of the energy is kinetic. So in other words, the spring is fully compressed or the spring is fully extended. The other important thing to note is that the total amount of energy, so this limit here, is going to be constant because there's no work being done by non-conservative forces, such as friction or somebody actually pushing this thing. And in theory, this glider should be able to bounce back and forth between these points forever. All right, for any graph of the potential energy versus x, the corresponding force, Fx, is equal to the negative of the partial derivative of that function, partial x. So partial u, partial x, the negative of that is the force. And that is the slope of the tangent line to the curve at that point. So if we wanted to look at what the force was at a particular point, what we could say is that it's the slope. That's going to be force. Or that's going to be force. Or that's going to be force. All right. Whenever the slope of u is 0, the force there is 0, and this is what is called an equilibrium. So in theory, at this point, at point O, the force is actually 0, either from the spring or on the spring. This thing is still moving, so it still has energy, and very soon it's going to actually create a force on it. So essentially you're sliding up to that neutral point. At the neutral point, there is no force. Beyond it, however, there is a force going this way. There's a force that's going to try to restore the spring and restore the glider back to that neutral position, whatever this neutral position. But at that 0 point, there is actually no force on the spring or from the spring. But outside of that, there is going to be a force, and that's going to try to restore the glider to its neutral position. Similarly, if we have the glider coming back this way towards the neutral point, it gets past the neutral point, it begins compressing the spring. The spring is now going to be exerting a force that way, back towards neutral. All right? But at the equilibrium point, which is point O, the force there is 0. So that's a very important concept, which is why I've emphasized it a bunch of different times and said this a bunch of different ways. When u is at a minimum, the force near the minimum draws the object closer to the minimum, so it's called a restoring force, and this is called a stable equilibrium. We'll have some good illustrations of what I mean by stable and unstable equilibria in a moment. And when the potential energy is at a maximum, the force near the maximum draws the object away from the maximum, which is called an unstable equilibrium. All right. So there you go. Here's perhaps a more sort of visceral and sort of more obvious example of a stable and unstable equilibrium. This is an unstable equilibrium. This is balancing rock. We met it in part 1 of this lecture series. So this rock is not currently going anywhere. It's stuck there. It's been stuck there for perhaps millions of years. However, eventually, this thing is going to get eroded away. The base is going to get eroded away, and it's going to lose its potential energy in a really big hurry. So while this equilibrium may be temporarily stable, the forces acting on this rock are going to eventually cause it to lose its potential energy and fall to Earth. So this is an example of an unstable equilibrium. How about a stable equilibrium? Well, I took an onion and I put that onion inside the bottom of a bowl. If I take some force and I disrupt the onion and I try to push it up the bowl, what's going to end up happening is that gravity is going to pull the onion back down towards the center of the bowl. So this would be the force of, oh my, that does not show up very well. Let's try this in black. So the force of gravity is going to try to get this back towards a stable equilibrium when this equilibrium is disturbed. So that's an example of a stable equilibrium. The onion is going to try to fall towards the center of the bowl when this equilibrium is disturbed. On the other hand, when it comes to balancing rock, if I were to apply a force to it, let's say that I were to push it this way, the reaction of the system would be toward minimizing the amount of potential energy. So in this case, let me just redraw this so that it's very clear. So I'm going to draw a disturbing force in black. So this is a force of disturbance. We're going to call it FD. And here, let's say that I were to push this, and this was once again a disturbing force, FD. The response of the system to that force, I'm going to outline in red. What will happen with the system in the unstable equilibrium case is a rapid loss in potential energy. All right? But in the case of the stable equilibrium, what's going to happen is, once again, a rapid loss in potential energy. But in this case, it's pulling us back to the starting state of that equilibrium, whereas here, the equilibrium has changed. In other words, the state of this rock has changed when a disturbing force is applied. Whereas in the stable equilibrium, when this disturbing force is applied, it tends to restore the stable equilibrium. So I don't want to beat a dead horse a little bit. I don't want to beat the dead horse too much, but just remember, this is an unstable equilibrium because a force will tend to change the equilibrium. This is a stable equilibrium because the disturbing force will tend to be canceled out and we will restore that equilibrium. Okay, so let's take an example of a particle moving along the x-axis when acted on by a single conservative force parallel to the x-axis. The force corresponds to the potential energy function graphed in the figure, figure 1, and the particle is released from rest at point A. So what is the direction of the force on the particle when it is at point A? The slope here is negative, right? So if we take the derivative at point A, the slope is negative, which means that F is positive. It means the force is positive. Or alternately, potential energy is decreasing, meaning that the force is increasing. At point B, the slope is positive, so F is negative. Remember that the sign of the force and the sign of the slope are going to be opposite. In part C, it's asking you, at what value of K is the kinetic energy of the particle at a maximum? So what we have to remember is that the total energy in this system is equal to the kinetic energy plus the potential energy, which is going to be a constant. And if we are asked to maximize K, what that means is that we have to minimize U. So K is max when U is min. And that occurs at x equals 0.75 meters, which is the global minimum of the potential energy function. That's right here. So again, that global minimum is going to be where the kinetic energy is highest. right? So in the next problem, it's asking us, what is the force on the particle when it is at point C? Well, the slope here is 0. That's a local maximum. And actually, in this case, it would be the absolute maximum of this potential function. So the force is equal to 0 as the slope is 0. All right? And then what is the largest value of x reached by the particle during its motion? Basically, we're saying, all right, the function extends up to here. So I'm sorry, this would be the absolute maximum, and then this would be the absolute maximum over here. This would be a local maximum. So I know I said this would be the absolute maximum. That's not true. The absolute maximum is here and here. All right, so what's the largest value of x? That's going to be where the potential energy is highest, which is therefore where the kinetic energy is lowest, or 0 in this case. And that corresponds to about 2.2 meters when you were looking at this particular graph. Right? What values of x correspond to points of stable equilibrium? So the stable equilibrium is going to be where you have the two minima of potential energy. That's going to be basically the bottom of the bowl. And you can kind of think of the bottom of the bowl as being the bottom of the potential energy function. So that's going to be here, and that's going to be here. So that's at 0.75 meters, and at 1.9-ish, 1.9 meters. Those would be the two minima and the 2 points that correspond to stable equilibrium. Of an unstable equilibrium, the point here would be the one maximum at 1.4 meters. So this would be at point C. This is an unstable equilibrium, right? Where the slope is 0 and where the potential energy is highest, where the slope is 0. Okay. So that's all, folks. That's Chapter 7 for you. I'd like to invite you to tune in next time for Chapter 8, where we will be covering momentum, impulse, and collisions. So you can finally begin to understand what happens when you're shooting pool. Thanks very much, and I will see you next time.